I am Amrita from Department of Electronics and Communication Engineering. My tech talk topic for satellite communications, where course code is AECD25, is the topic name is Explain Orbital Mechanics and List Various Orbital Elements. Introduction to Orbital Mechanics. Orbital mechanics, also known as celestial mechanics, is the study of the motion of objects in space under the influence of gravitational forces. It explains how planets, moons, satellites, and spacecraft move around celestial bodies. Understanding orbital mechanics is essential for satellite deployment, space missions, and predicting celestial events. Historical background. The study of orbital mechanics dates back to Isaac Newton's law of motion and universal gravitation. Johannes Kepler formulated three laws describing planetary motion in the early 17th century. These foundational principles laid the groundwork for modern space navigation and satellite technology. Basic concepts in orbital mechanics. Orbits are the paths that objects follow around a central body due to gravitational attraction. The shape, size, and orientation of an orbit depend on initial velocity and position. Key concepts include velocity, acceleration, and gravitational potential energy. So, these are the objects in the orbital mechanics are the paths where orbits are the paths where the object follow around the central body due to attraction of the gravitational motion. And the shape, size, and the orientation of an object depend on the initial velocity. Types of orbits. Circular orbits have a constant radius and speed, maintaining a fixed distance from the central body. Elliptical orbits are elongated and characterized by two focal points, with one usually at the center. Where one focal point is usually at the center. Other types include parabolic and hyperbolic trajectories, which are escape or inbound paths. Kepler's laws of planetary motion. First law states that planets move in elliptical orbits with the sun at one focus. Second law. The law of equal areas indicates that a line connecting a planet and the sun sweeps out equal areas in equal times. Third law relates the orbital period to the size of the orbit, specifically the semi-major axis. These are the laws of the Kepler's. Newton's law of universal gravitation. Every two masses attract each other with a force proportional to their masses and inversely proportional to the square of the distance. This gravitational force governs the motion celestial bodies and satellites. It provides the mathematical basis for calculating orbital trajectories. Orbital elements overview. Orbital elements are parameters used to simplify, define, an orbit in space. Provide a mathematical description of an orbit's size, shape, and orientation. These elements are essential for mission planning, navigation, and tracking. Semi-major axis A. The semi-major axis defines the size of an elliptical orbit, representing half the longest diameter. It determines the average distance of the orbiting objects from the central body. The orbital period is directly related to the semi-major axis through Kepler's third law. Eccentricity E. Eccentricity measures the deviation of an orbit from a perfect circle. A value of 0 indicates a circular orbit, while values approaching 1 indicate highly elongated ellipses. It influences the orbital speed variations along the path. Inclination I. Inclination is the angle between the orbit plane and the reference plane, usually the equatorial plane. It determines the tilt of the orbit relative to the planet's equator. Inclination affects ground coverage and visibility of satellites. Write ascension for the ascending node. It specifies the angle from a reference direction, usually the vernal equinox, to the ascending node. The ascending node is where the orbit crosses the reference plane from south to north. These elements defines the horizontal orientation of the orbit. Argument of periapsis. The argument of periapsis measures the angle from the ascending node to the orbit's closest approaching point. It indicates where the closest point to the central body occurs within the orbit. This element helps to determine the orientation of the orbit within its plane. True anomaly. True anomaly is the angle between the periapsis and the current position of the orbiting object. It varies as the object moves along its orbit. It is used to specify the exact position of the satellite at a given time. Other orbital elements. Mean anomaly, which relates to the position in the orbit as a function of time. Eccentric anomaly, an auxiliary angle, is used in orbital calculations. These elements assist in precise orbit determination and prediction. Orbital mechanics in satellite deployment. Accurate knowledge of orbital elements ensures proper satellite placement and operation. Adjustments to elements are made after launch to achieve desired orbits. Maintaining and controlling orbital elements is vital for mission longevity. Applications of orbital mechanics used in designing space missions, satellite constellations, and planetary exploration, critically for collision avoidance and space debris management. Supports navigation systems like GPS and Earth observation satellites. Challenges in orbital mechanics. Perturba- Perturbations and gravitational influences complicate orbit prediction. Orbit decay requires station keeping maneuvers for low Earth orbit satellites. Accurate modeling demands computational resources and detailed data. Coming to the future trends and technologies, advancements include autonomous orbit determination and correction systems, increased use of machine learning for orbit prediction and management, emerging propulsion technologies enable more precise and more suitable orbital operations. Coming to the summary and conclusion, orbital mechanics provides the fundamental principles governing space object trajectories. Understanding orbital elements is essential for effective space mission planning. Ongoing research and technology continue to enhance our capabilities in space navigation. Thank you.